At 8:11 UTC on the morning of November 29, 2025, a Level 3 anomaly report was quietly issued within NASA's Planetary Defense Coordination Office. It wasn't labeled an impact threat. It didn't trigger the public-facing asteroid alert protocols, but it did initiate an internal escalation chain. The subject was 3I Atlas, the interstellar object already under continuous observation since early July. The reason was a subtle, almost imperceptible lateral deviation in its trajectory, not the kind of drift caused by thermal outgassing or gravitational nudges. This one showed signs of directed movement. It wasn't large, but it was precise, and it was the second such shift in less than 10 days. To most, this might sound like an overreaction. Celestial bodies shift all the time. Orbits evolve. Forces act on comets from all directions. Solar wind, radiation pressure, outgassing. But this wasn't noise in the data. This was vector-aligned acceleration pointing toward a specific sector of Earth's orbital shell. The tracking software, which runs probabilistic models on thousands of solar system objects, marked the anomaly with a red flag. Internal logs from the Deep Space Surveillance Network confirmed that the object's acceleration was consistent with a controlled adjustment, and that was enough to trigger an alert. It's important to understand that NASA's planetary defense system isn't just looking for collisions, it also monitors for behaviors, for patterns, for actions that imply intent, or at the very least, unnatural coordination. When an object's motion profile begins to resemble something that is compensating for inertia, or aligning with orbital inclinations that no passive body should track, the algorithms flag it. This is precisely what happened on November 29. The shift was only a fraction of a degree, but it was enough, not because of the magnitude, because of the geometry. 3 independent observatories fed triangulated telemetry into the system that morning: Haleakala in Hawaii, La Silla in Chile, and the NEO surveillance node in southern Italy. Each one reported consistent vector realignment toward the 0.987 AU band, a region coinciding with Earth's position in its elliptical path. This by itself would not have been alarming. But when cross-referenced against the object's prior acceleration patterns already deemed non-gravitational and asymmetric by the International Astronomical Union, the situation changed. The alert did not suggest impact. The model still showed a safe miss distance, well outside any planetary defense threshold. But the deeper concern wasn't collision, it was coherence. The object was exhibiting something comets aren't supposed to: repeatable, symmetrical course adjustment behavior. This wasn't random tumbling or sun-triggered venting, it was structured, and it was escalating. Within minutes, the internal system protocols activated a secondary confirmation. The US Space Force's Space Surveillance Squadron received a request for passive tracking. ESA's Gaia mission, already aligned with the object's rough coordinates, was silently tasked to scan for optical signature changes, and within 1 hour the National Space Council received a quiet heads-up. 3I Atlas had made another move, not a big one, but a directional one. What makes the November 27th signal especially consequential is not its danger, but its implication. Because it suggests that whatever 3I Atlas is, it may no longer be moving passively through our solar system. It may be responding to something, possibly internal, possibly environmental, possibly intentional. From that moment forward, every orbit prediction was recalculated, every spectral scan was reanalyzed, and the planetary defense teams across NASA, ESA, and JAXA entered a state they rarely talk about publicly: observational escalation. Not panic, not protocol breach, just focus, intense, silent focus, because the signal had arrived, and it came not from a transmission, but from motion. To understand why planetary defense protocols were triggered on November 29th, we need to begin with what those protocols are designed to detect, and what they are not. Contrary to public assumption, NASA's Planetary Defense Coordination Office does not wait for imminent impact warnings to respond. The system is designed to monitor an entire spectrum of anomalous behaviors, and one of the highest priority flags in that system isn't an object on a collision course, it's an object behaving like it shouldn't be. That's what made 3I Atlas different. The interstellar object, officially designated the third of its kind after Oumuamua and 2I Borisov, had already shown signs of irregular motion weeks prior. Spectral data revealed a volatile mix of carbon dioxide and exotic dust signatures, But it was the kinematics that drew the most scrutiny. Observatories began noticing deviations in its motion, not explained by gravitational interactions alone. Normally, such deviations can be written off as the result of outgassing, a phenomenon where sunlight causes subsurface ice to vaporize, pushing the object with small bursts of natural thrust. But in this case, the outgassing models didn't match the observed acceleration. There were no symmetrical jets, no debris fields, and the changes in trajectory weren't random, they were linear. They followed clean arcs, with angular consistency over time. The same regions of the object appeared to fire, if we can call it that, during multiple observational windows. This implied the presence of stability, not chaos, coordination, not randomness. By November 25th, the object had already made one such adjustment. A secondary shift was detected on November 28th, but it was the third change, on the morning of November 29th, that crossed a threshold. The object had subtly reoriented, again, but this time directly into alignment with Earth's orbital path, not in terms of collision, but parallel co-orbital drift. It was now falling into a region that placed it in long-term tracking proximity with our planet's orbit. In most cases, that wouldn't mean much. But when an object from outside the solar system begins matching inclination to within tenths of a degree, the system flags it. And when that alignment happens with less than 1% deviation over 3 sequential shifts, it triggers escalation. The protocols are tiered. Level 1 is passive tracking. Level 2 is coordinated multi-instrument confirmation. Level 3, which is what was triggered that morning, initiates a shared alert between defense-related space agencies. It doesn't mean an object is dangerous, it means it's behaving with too much precision to be ignored. Within minutes of the alert, the Deep Space Network realigned its radar array in Goldstone, California. Not to fire signals, but to listen, to check for reflections, subtle delays, signature inconsistencies. Meanwhile, NASA's Near-Earth Object Wide Field Infrared Survey Explorer, NEOWISE, was directed to refresh thermal imaging parameters. It had already shown the object emitting at levels higher than expected for passive sublimation. What they were looking for was confirmation that the object's motion wasn't just reactive, it was proactive, and that's the distinction that matters, because most natural bodies respond to their environment, but they don't anticipate it, they don't correct mid-path, they don't reduce deviation in real time, and they don't realign their trajectory 3 separate times in geometrically refining vectors unless something inside is doing the aligning. That's why Planetary Defense responded, not because 3i Atlas was going to hit Earth, but because it moved like something that could choose to. And that, for any planetary defense system, no matter how advanced, is enough. When 3i Atlas made its third deviation on the morning of November 29th, it wasn't the size of the course correction that raised alarm, it was the precision. The adjustment was just 0.06 degrees in trajectory arc, a movement almost imperceptible to the casual observer. But to the network of observatories tracking the interstellar object, it was unmistakable. This wasn't drift, this was control. That word, control, isn't used lightly in orbital dynamics. Most celestial bodies are at the mercy of gravitational wells, radiation pressure, and thermal venting. Their paths are calculated through equations that presume passivity. They do not navigate, they do not choose. But the motion profile of 3i Atlas was beginning to show patterns that couldn't be explained by chance or by the sun's uneven heating of its surface. After the second course adjustment was detected on November 28th, researchers began running simulations. Using known comet behavior, they tried to reproduce the object's current trajectory by inputting combinations of asymmetric outgassing and rotational acceleration. None of the models aligned with what had actually been observed. To match the movement, a natural comet would have required sustained high-velocity jets firing from fixed locations on its surface over multiple days. But spectroscopic imaging showed no such venting, no visible emissions, no gas cloud expansion, no debris trails. In every measurable wavelength, the object appeared quiet, but the math said it was moving. The third course correction, which occurred at 0807 UTC, was measured using a combination of long baseline parallax imaging and Doppler velocity readings. The parallax was verified independently by 3 observatories in different hemispheres. When all 3 readings were plotted, the arc of motion wasn't just reactive, it appeared optimized. a correctional thrust that reduced the object's angular deviation relative to Earth's orbital plane by over 40% compared to its previous path. In orbital mechanics, this is what's known as an efficient delta V, a low-energy adjustment that maximizes positional effect over time. And it was precisely that kind of efficiency that caught the attention of mission planners. This kind of correction is not something comets do, it's something spacecraft do. It's how we course correct during deep space maneuvers. Small nudges, delayed impact, maximum effect. Avi Loeb, the Harvard astrophysicist who gained global attention for his analysis of Oumuamua, responded to the data within hours. In an off-the-record quote leaked by one of his graduate researchers, he reportedly said, "That's not tumbling ice, that's trajectory logic." When asked later about the comment, Loeb declined to confirm, but emphasized that the motion could not yet be attributed to known physics without invoking external assumptions. Some scientists pointed to the possibility of delayed thermal lag, subsurface ices venting long after initial sunlight exposure. Others suggested the effect might come from a rotational moment coinciding with a radiation asymmetry. But even those more conservative explanations required perfect timing. A spontaneous acceleration vector aligning with a precise decrease in solar distance without any visual evidence of venting is unlikely. The odds compound with each shift. In the wake of the third correction, internal emails circulated within the European Space Agency suggested initiating temporary cross-correlation with space weather satellites, specifically looking for any electromagnetic disturbances in the object's vicinity. None were found. So the question deepened. If this wasn't an effect of the solar wind or radiation or outgassing, what was it? The term course correction may sound innocuous, but in astrodynamics it implies an understanding of future position, an anticipation of movement. Something is adjusting this object, not randomly, but strategically. The third correction sealed it. It didn't alter the probability of an Earth encounter, but it proved something more important, that 3i Atlas is not just travelling, it's navigating, and no one expected that. When 3i Atlas began showing signs of directional acceleration, many in the scientific community found themselves revisiting the first interstellar anomaly that set the precedent for all others, Oumuamua. First detected on October 19, 2017, Oumuamua was the first confirmed object to enter our solar system from interstellar space. It moved fast, entered on a hyperbolic orbit and left just as quickly. But what made it unforgettable was not its origin, it was its behaviour. Oumuamua, like 3i Atlas, defied basic expectations of how a comet or asteroid should behave. It had no visible tail, no coma, and no gas emissions detected by any observatory. Yet it accelerated. Slightly, persistently, and unnaturally. At the time, scientists searched for natural explanations. One hypothesis suggested that outgassing of hydrogen ice could create motion without producing visible signs. Others leaned toward delayed sublimation or solar radiation pressure acting on a strangely shaped body. But nothing fully accounted for the acceleration without requiring extremely specific assumptions. Dr. Avi Loeb, then chair of Harvard's astronomy department, made headlines and enemies when he suggested a bold alternative, that Oumuamua might have been a piece of alien technology, possibly a light sail or a fragment of something artificial. The mainstream response was largely dismissive. Peer-reviewed papers flooded in offering counter-theories, but none of them completely invalidated Loeb's calculations. They merely proposed slightly more comfortable maybes. The legacy of Oumuamua didn't fade because it was resolved. It faded because it exited. We simply never got another look. But 3i Atlas is different. It's still here, still accelerating, still within observational reach, and that makes the comparison unavoidable. Both objects originated from interstellar space. Both moved on hyperbolic trajectories that confirmed they were not gravitationally bound to the Sun, and both displayed anomalous accelerations without corresponding evidence of outgassing. But there's a key difference in timelines. Oumuamua was visible for just 11 days before it faded from telescope range. 3i Atlas has been under constant observation for months. This gives us what Oumuamua never could, long-term behavioural data. As researchers began to detect trajectory deviations in 3i Atlas, many returned to the 2017 Oumuamua analysis as a framework, not because they believed the two were identical, but because the patterns were eerily familiar. The difference is that this time, we were ready. In 2017, there were no standardized alert tiers for interstellar anomalies, no real-time cross-agency data synchronization. Oumuamua forced the scientific world to retrofit its protocols after the fact. In its wake, NASA and the European Space Agency quietly integrated interstellar object triggers into planetary defense systems, frameworks that wouldn't have existed without the confusion Oumuamua caused. The 2017 framework also introduced the idea that if we encountered another object with similar properties, we should prioritize observing its changes, not just its composition. That protocol is exactly what led to the November 29th response. In many ways, 3i Atlas is the stress test of what the 2017 framework put in place. It's behaving more boldly, it's moving closer, and unlike Oumuamua, it isn't fading, it's evolving. The debates from 2017 are now resurfacing. Is this solar heating acting on unknown volatiles? Is this low-velocity thrust from trapped gases buried under a crust? Or is it something that responds to orbital mechanics the way a probe or sailcraft might? Revisiting Oumuamua reminds us that science doesn't move in straight lines. It moves in loops. It revisits old questions with new tools. And right now, 3i Atlas is demanding that we reopen the file marked unresolved. Because the object we're watching now is not just another visitor. It is, perhaps, the continuation of a conversation that began in 2017 and never really ended. When astronomers talk about celestial trajectories, they speak in terms of orbital inclination, eccentricity, and perihelion distance. But what often matters more, especially in planetary defense, is something far simpler: alignment. In the days leading up to November 29th, analysts noticed a quiet but consistent trend in the orbital evolution of 3i Atlas. It was flattening. More precisely, its trajectory was bending, slowly, steadily, toward Earth's orbital plane. Known as the ecliptic, this invisible disk is where nearly all planetary bodies travel, including Earth, Venus, and Mars. The solar system, for all its chaos, is surprisingly flat, and when something from outside that plane begins to align with it, scientists pay attention. 3i Atlas didn't begin this way. When it was first detected, its approach vector placed it several degrees above the ecliptic, consistent with an interstellar origin. Hyperbolic objects entering from deep space rarely follow the neat plane of our solar system. They come in steep, cutting through at sharp angles. That's what made its gradual realignment so peculiar. Instead of maintaining its steep path, 3i Atlas began to coalesce. Its angle of approach decreased, not dramatically, but measurably. From an initial inclination of 19.6 degrees, it dropped to 17.1, then 14.8. And by November 29th, it had reached 12.4 degrees. In isolation, this might not raise flags. Comets can shift due to solar radiation, tidal forces, or jet activity. But 3i Atlas wasn't displaying the outward signs of any of these phenomena. Its coma remained faint, its tail nearly absent. Spectral scans showed no significant venting or fragmentation. Yet the orbit kept bending. It was behaving, again, as if it was steering. Orbital dynamics tells us that even small trajectory changes at interplanetary distances produce enormous course alterations over time. A 1-degree change now can translate to millions of kilometers later. So when an object gradually adjusts itself to follow Earth's orbital path, scientists aren't looking for impact, they're looking for behavior. The alignment wasn't perfect. 3i Atlas wasn't merging into Earth's precise position or mimicking its velocity. But the inclination was dropping toward co-orbital territory, an orbital zone where shared motion becomes gravitationally sensitive. These zones are rare and unstable. Natural objects rarely remain in them, unless they're captured or disrupted. And 3i Atlas seemed to be nudging into it voluntarily. Models from the Jet Propulsion Laboratory showed that if the trend continued, the object's orbital plane would cross within 1.6 degrees of the Earth's path by December 10th. Not close enough to suggest collision, but close enough to suggest synchronization. And synchronization is not a behavior of chaotic bodies. There is historical precedence for this kind of attention. In 1994, comet Shoemaker-Levy 9 fragmented and impacted Jupiter in a sequence of co-orbital strikes. Before the event, its path curved into Jupiter's orbital band, a deviation that made its ultimate trajectory more than coincidence, astronomers remember. And they watch for patterns that echo that memory. For 3i Atlas, the bending trajectory is not about threat, it's about decision. The physics required to alter an incoming interstellar path into alignment with Earth's orbital shell are enormous. It requires both timing and anticipation. Natural processes, no matter how complex, rarely produce such focused drift without significant external input. If the motion was driven by outgassing, we should see jets. If it was caused by gravitational interactions, we should see perturbation signatures. Instead, we see silence and movement. In astrodynamics, alignment is the language of intent. It's how spacecraft insert themselves into flybys or orbital slingshots. It's how satellites synchronize. It's how probes return home. So what does it mean when a supposedly natural object from another star system begins bending its path to follow ours? We don't know yet. But nature doesn't usually write in straight lines. It spirals. And now, so does 3i Atlas. To understand the anomaly that is 3i Atlas, we must first understand how natural objects drift within the gravitational well of the Sun. In heliocentric motion, the movement of objects around the Sun, there is an expected rhythm. Comets and asteroids follow elliptical or hyperbolic paths, shaped by gravity, perturbed slightly by solar radiation pressure, and sometimes nudged by outgassing. But even with these complexities, most small bodies in our system follow predictable orbital mechanics. They spiral inward, accelerate as they approach the Sun, and arc away along a mirror path. 3i Atlas does not follow that script. When analysts mapped the motion of 3i Atlas across its heliocentric arc, they noticed a quiet but unmistakable divergence. Its trajectory did not follow the clean curve of a gravitational infall. It wobbled, very slightly but consistently. Instead of flowing with the elegant gravity of the system, it exhibited small lateral deviations. These weren't random jitters or noise in the signal. They formed a pattern, a drift that looked reactive, and over time that pattern defied every natural expectation. Normally, outgassing causes jets to erupt from surface fissures, imparting gentle thrust. If a comet is spinning, those jets can create complex but mappable changes in velocity, often causing a precession in trajectory. But 3i Atlas did not display precession. Its motion didn't spiral outward, it shifted laterally, almost as though it was repositioning. These heliocentric drift patterns became most evident in late November, during the post-perihelion phase when the object began moving away from the Sun's closest approach. The Solar and Heliospheric Observatory, SOHO, which had been capturing wide-field images of the comet's approach, recorded position data that diverged by nearly 0.03 degrees from projections made just 10 days earlier. That may sound minor, but in orbital mechanics, even a micro-degree of drift, when sustained, compounds over millions of kilometers. The anomaly wasn't that it drifted, it was how it drifted. Natural drift, whether caused by radiation pressure or sublimation, should bias outward. The Sun's energy pushes particles away, causing tails to stretch and orbits to distort in the direction opposite the Sun. But 3i Atlas's shift wasn't radial, it was tangential, along the orbital path, not away from it. This kind of motion implies active propulsion, or at the very least an internal guidance mechanism capable of shifting velocity vectors in alignment with heliocentric coordinates. Even more telling was the consistency of the change. It wasn't abrupt, it didn't spike, then settle. It evolved gradually, over several observation windows. Scientists at the European Space Agency ran Monte Carlo simulations using over 2 million input variations for gas venting locations, thermal lag, nuclear spin rate, and solar vector orientation. None of the models reproduced the smooth lateral adjustment. Every output required either noise injection or extreme values for mass loss asymmetry, values that no spectral data supported. In a joint statement released internally to collaborating research institutions, the ESA referred to the phenomenon as directional drift coherence. It's a term rarely used outside of deep space propulsion modelling. It means that the object's motion is not just reactive, it appears to be governed by an internal equilibrium model, something that keeps it on a specific path relative to solar motion. This is not behaviour we've ever observed in a natural object. Even when accounting for mass, rotation and solar interaction, nothing explains why 3i Atlas is bending its heliocentric path in smooth lateral arcs. No dust plume, no irregular outburst, just motion, calculated, coherent, and sustained. And so the question deepens. Is this just an extreme case of non-gravitational acceleration, or are we watching the first known object from outside our solar system navigate the Sun's gravitational field with purpose? In the early hours of November 29, 2025, following the third unexplainable course correction by 3i Atlas, a set of internal communications began circulating within the Planetary Defense Coordination Office. These were not formal press releases or public data drops. These were internal logs, coded transmissions, and encrypted emails exchanged between key mission directors, orbital analysts, and external scientific partners. The subject line of one now-leaked email read simply, "This isn't just outgassing." The message was authored by a propulsion modelling specialist at NASA's Jet Propulsion Laboratory. The recipient list included senior staff from the Near-Earth Object Observations Program, the Goddard Space Flight Center's Heliophysics Division, and 2 liaisons from US Space Command. The body of the email was short, direct, and free of speculation. It included a table showing delta-V anomalies recorded between November 23rd and November 29th, broken down by vector axis and magnitude. What caught everyone's attention was not just the accuracy of the data, it was the conclusion attached to it. The object's cumulative velocity shift over that period could not be accounted for by any known form of sublimation or venting. Not unless one assumed a combination of buried supervolatiles, exotic rotational patterns, and coordinated surface exposure, all of which were unsupported by infrared or ultraviolet scans. The email posed a simple hypothesis. If this were a spacecraft using controlled microthrust, this is the delta-V pattern we'd expect. In the hours that followed, more communications began surfacing. A senior analyst at the Applied Physics Lab echoed the concerns. "We are not observing chaotic release," she wrote. "We're observing consistent directional motion. The object's rotational phase isn't shifting between burns. The corrections are stabilizing, not randomizing." This is a crucial distinction. When comets release gas from heated surfaces, the resulting thrust is uneven and varies as the body rotates. This creates a tumbling signature, a kind of unpredictable wobble. But 3i Atlas was not wobbling, it was stabilizing. Each drift vector appeared to reduce its previous angular momentum, not amplify it. This suggested not only active correction, but feedback, as if the object was compensating for its own movements. Further email exchanges between the Orbital Mechanics Division at Langley and NASA's Goddard team began referencing what they called patterned thrust intervals. Using Doppler telemetry, they identified at least 4 segments of motion where changes in velocity occurred in smooth arcs over roughly identical durations. These segments did not align with peak solar radiation exposure or perihelion points, further weakening the outgassing explanation. This wasn't a one-time event, it was a pattern. In one of the more candid exchanges, a propulsion specialist wrote, "We are past the point of modelling ice vents. This looks like station keeping." The term station keeping refers to the practice of using small propulsion bursts to maintain a spacecraft's position relative to an orbit or trajectory. It's common among satellites, it's standard in deep space probes, but it's not part of cometary physics. At this point, discussions turned cautious. The term artificial was never written outright in official threads. But euphemisms appeared. Non-natural correction events, coherent vector intervals, exotic control schema. These are the linguistic shadows of a scientific culture unwilling to jump to conclusions, but deeply aware of what it's seeing. By midday, NASA had convened a quiet roundtable among its most senior planetary defense advisors. The conclusion? Continue observation, increase spectral scans, maintain silent escalation posture, no public alerts, no press briefings, just eyes on. Because whatever was moving, 3i Atlas was no longer behaving like physics alone could explain. And deep inside the agency, some had already accepted what the math was showing. This wasn't just outgassing, this was something else. On the morning of November 29th, 2025, less than 4 hours after the confirmed trajectory shift of 3i Atlas, 2 ground-based observatories, one in southern Spain, the other in northern Argentina, initiated synchronized radar ping experiments. These stations, part of a collaborative planetary radar network supported by the European Space Agency and the South American Deep Space Array, had tracked previous cometary bodies before, but this was different. They weren't passively observing, they were actively probing. The objective was simple: bounce a radar signal off 3i Atlas and analyze the return. This technique, known as bistatic radar imaging, is typically used to determine the shape, rotation, surface texture, and relative velocity of near-Earth objects. It works by transmitting a beam of radio waves from one station and receiving the reflection at another location, often on a different continent to capture a broader geometry. Spain transmitted, Argentina received. The window for the operation was tight. At that point in its trajectory, 3i Atlas was not optimally aligned for long-distance radar experiments, but its relative proximity, within 1.9 astronomical units, and slow radial drift made it just viable. The stations were equipped with high-gain antennas operating in the X-band, optimized for fine detail echo resolution. They expected a weak signal, perhaps a blurred reflection depending on the object's size, spin, and composition. What they received instead left both teams stunned. The echo returned almost instantly, far stronger than anticipated and far more coherent. The signal exhibited an unusually sharp polarization, indicating that the surface it reflected off was not irregular and diffuse like typical cometry material. Instead, the surface appeared flat, possibly metallic or crystalline in texture. It behaved less like frozen dust and more like a structured boundary. This alone was enough to trigger a round of internal analysis. But then came the Doppler echo. Radar returns carry within them a frequency shift, a change caused by the movement of the reflecting object relative to the source. This Doppler data can be used to estimate velocity and, in some cases, spin. The Argentinian station measured the shift and found it inconsistent with expectations for a tumbling comet. Instead of a randomized spin signature, the return showed a tight symmetrical band, implying rotation, yes, but not chaotic. It was consistent, stable, controlled. More surprising still was the presence of a secondary echo. Roughly 2.1 seconds after the main return, a fainter but structured echo bounced back from a slightly different location. When triangulated, the second signal appeared to come not from the nucleus of the object, but from something trailing it by approximately 1.6 kilometers. A debris fragment? A separated lobe? Possibly. But the signature was unusually clean, with a high signal-to-noise ratio and an identical Doppler slope. That suggested not random debris, but something moving in near-perfect synchrony with the main body. This finding prompted further scans. Multiple ping sequences were run throughout the day, and while weather conditions degraded the signal briefly, the pattern held. A consistent echo, a trailing component, a non-chaotic spin profile, and a primary structure that did not scatter the radar signal the way ice or dust would. Both facilities submitted preliminary findings to the International Astronomical Union late that evening, under the classification Anomalous Radar Return. Privately, however, their reports were more direct. "This is not a comet," read the handwritten note appended to the official radar plot from Spain. "This is a vehicle, or at least it reflects like one." The teams were instructed to remain silent. No press releases, no conferences. But within the scientific radar community, the implications spread rapidly. Because if a structured object is returning coherent radar echoes, and it's drifting deliberately toward Earth's orbital plane, then we may not just be tracking it, it may also be tracking us. At a distance of nearly 270 million kilometers, thermal detection of small interstellar objects is not straightforward. Most comets, especially those beyond Earth's orbit, are faint in infrared. They release sublimated gases, primarily water vapor, carbon monoxide, and carbon dioxide, that generate weak thermal emissions, barely above background radiation. But on the evening of November 29, 2025, the Near-Earth Object Wide-Field Infrared Survey Explorer, better known as NEOWISE, recorded something that stunned its operators. 3i Atlas was glowing. Not metaphorically, thermally. The signal was picked up as part of a targeted scan designed to reassess the object's surface composition. NEOWISE's instruments are tuned to detect thermal radiation between 3 and 22 microns, which allows scientists to estimate the temperature of space objects by measuring how much infrared energy they emit. Comets, when active, show signatures in these wavelengths due to sublimation processes, but inactive or dormant comets, especially those at this distance, should not. 3i Atlas wasn't just active, it was emitting a signature so strong it rivaled some near-Earth asteroids. The initial analysis placed the thermal emission equivalent temperature between 154 and 160 Kelvin. That's roughly minus 115 degrees Celsius, still cold by human standards, but far too warm for a supposedly passive interstellar object at nearly twice the Earth-Sun distance. And more importantly, the distribution of that heat was wrong. Most comets show thermal hotspots concentrated on their sun-facing hemisphere, the side being bombarded by solar radiation sublimates, releasing gas and heating the surface. But in the case of 3i Atlas, the infrared imaging showed a concentrated band of thermal intensity along a narrow equatorial ridge, an area not consistent with expected solar heating angles at that time. In simpler terms, it was glowing from the sides. That thermal ring, distinct, narrow and stable, across multiple orbits, suggested an internal mechanism, perhaps a latent radioactive decay process, perhaps residual heat from deep crust activity, or perhaps something more organised. Scientists attempted to explain the anomaly using known natural processes. Some proposed frictional heating caused by rotational shear, where the body spins and internal layers rub against one another, releasing heat. Others modelled theoretical crystallization of amorphous ice within the nucleus, which can release thermal energy as it converts into a more stable state. But these explanations fell short when matched against the data. For crystallization to explain the heat, it would need to occur uniformly across a narrow ring, something not observed in any known comet. For rotational shear to fit, the object would need to spin with a torque signature detectable by its light curve. But 3 Atlas's brightness had remained flat, with no periodic modulation, no flashing, no dips, no pulsation. It wasn't spinning like a tumbling comet. It was rotating, yes, but smoothly, evenly, as if balanced. What this left, uncomfortably, was a heat source that did not appear to be responding to solar input. It was internal, stable, possibly regulated. Further complicating the issue was the presence of a secondary infrared hotspot, trailing the main object by roughly 1 kilometre. Neowise initially flagged this as background noise, but after 3 consecutive passes the anomaly persisted. It mirrored the main object's heat curve, but at a lower intensity, suggesting proximity and connection. Some began to ask what no one wanted to say aloud: is this residual heat from propulsion? Because the thermal symmetry, equatorial confinement, and sustained emission matched models more often used to analyse spacecraft, particularly those employing controlled ion-based or microwave propulsion systems, systems that radiate heat along fixed arrays, often along the spin axis. Comets are messy. Their heat signatures are chaotic, variable, and directionally biased. 3i Atlas was none of those things. It was calm, focused, and warm in places it should have been cold. Which begs the question, what's inside this object that keeps it warm, even when the sun says it shouldn't be? In astronomy, symmetry is usually a sign of distance, not design. Distant galaxies appear symmetric due to the blurring effects of scale. Planetary rings seem perfect until examined up close, and most comets, chaotic and violent in nature, never exhibit symmetry, because they are inherently unstable. So when a near-field interstellar object begins to show perfect, glowing, spherical symmetry, scientists know something is wrong, or at least unexplainably precise. That's exactly what began to appear in late November 2025. Multiple amateur astrophotographers, armed with nothing more than backyard telescopes and long-exposure tracking software, began capturing 3i Atlas with an unmistakable new feature, a glowing, symmetric field surrounding the object's core. It wasn't a coma, it wasn't a dust tail, it was something more consistent, an energy field that held shape across time and exposure. Professional observatories took notice. On November 28th, the Gran Telescopio Canarias released preliminary spectrographic slices from 3i Atlas's outer emissions. What they detected was deeply abnormal, a plasma signature consistent with low-energy ionization, specifically the presence of ionized oxygen, carbon, and an unusually elevated count of hydrogen beta emissions. These weren't random, they were layered, in radial bands. In comets, plasma tails form as solar radiation ionizes gases, sweeping them into long filaments opposite the Sun. But this was not a tail, It was a sheath, a nearly perfect spherical glow radiating evenly in every direction. That level of plasma containment cannot be explained by sublimation alone. More telling than the plasma presence was its uniformity. Instruments at the University of Tokyo's Institute for Cosmic Plasma revealed an emission uniformity index of 94.2%. That number is significant. Natural processes, especially outgassing, produce irregular, jagged plasma shells. This object's emissions were organized, concentric, and stable across multiple measurement windows, and they didn't trail behind, they surrounded. There is a principle in astrophysics known as equipotential collapse. It describes how plasma fields eventually diffuse under solar wind influence. The field around 3I Atlas wasn't collapsing, it was holding shape, which led scientists to consider a possibility both exciting and deeply uncomfortable: containment. Plasma containment isn't something nature does well on small scales, but humans try. Fusion reactors like ITER and Stellarator designs rely on powerful magnetic fields to hold plasma in symmetrical loops. Theoretically, an object capable of maintaining plasma symmetry in deep space would require embedded electromagnetic field generators, technology far beyond our current engineering limits. Was this what we were seeing, or was it something more exotic? Avi Loeb weighed in with a statement on November 30th. Plasma symmetry is not conclusive evidence of design, but it is rare, and when symmetry appears in regions where instability is expected, we should at least allow for hypotheses outside of what we've catalogued. Not everyone agreed. Several physicists proposed that the symmetry was an illusion, an artifact of over-processed images. But when ESA released their calibrated wide-angle imagery from the Lagrange Point 1 Solar Observatory, the same pattern emerged. Symmetry. Uniform glow. No tail. The glow was not just real, it was measurable, and that leaves us with a scientific dilemma. Either 3I Atlas has discovered a way to suspend plasma in defiance of every known thermal and magnetic principle we associate with comets, or it is not a comet at all. In science, symmetry is often dismissed as coincidence. But when that symmetry forms a plasma shell, and when that shell rotates with the object, stabilizes over time, and remains intact across millions of kilometers, then we have to ask the question we've avoided until now. What if this field wasn't emitted, but engineered? One of the most reliable methods for estimating a comet's behavior is by measuring mass loss. As sunlight hits the surface of a comet, ices sublimate, transforming from solid to gas and ejecting material into space. This outgassing causes visible tails, detectable gas spectra, and momentum transfer, which slightly alters the comet's trajectory. The faster the object accelerates, the more mass it must be losing. But 3I Atlas doesn't follow this equation. Beginning in mid-November, orbital tracking data from NASA's Deep Space Network confirmed that 3I Atlas was accelerating, not drastically, but consistently. Over a span of 14 days, the object's path deviated by over 4,000 kilometers from its projected course. Using Newtonian mechanics, that acceleration must be explained by a force, and, if it's outgassing, there must be mass loss. So scientists ran the numbers, assuming a nucleus between 500 meters and 5 kilometers in diameter, typical for comets of this brightness. The calculations revealed that to achieve the observed acceleration, 3I Atlas would need to lose between 2.3 and 8.1 million kilograms of material per day. That mass, ejected into space at comet-typical velocities, would create a vast debris cloud tens of thousands of kilometers wide, but that debris cloud doesn't exist. The Hubble Space Telescope, the James Webb Space Telescope, and a network of Earth-based observatories looked for it. They found no dense coma, no expanding gas shell, no photometric spikes indicating venting events. Instead, 3I Atlas remained clean, smooth, and eerily stable. This is the heart of what scientists are now calling the missing mass loss paradox. Acceleration is happening, but the expected consequences are not. Some researchers attempted to explain it using non-visual outgassing. Perhaps the object was venting transparent gases like hydrogen or helium, which do not emit strongly in the visible or near-infrared range. But even those would still leave signatures in ultraviolet, radio, or spectral scattering. None appeared. Others theorized a delayed venting model, where sublimated material builds pressure inside the object and releases in short, high-velocity bursts too fast to capture on camera. But those bursts would still leave thermal or rotational disturbances. Again, nothing was observed. That left one more possibility. The acceleration is not being caused by outgassing at all. In that case, what is propelling 3I Atlas? This is not an idle question. In physics, motion must come from force, and force must come from interaction, either internal or external. Without visible ejection of material, the only remaining sources are internal propulsion, gravitational slingshot effects, or environmental interaction with forces we have not yet mapped. Gravitational influence was ruled out. No planetary body or known mass passed near the object during the acceleration phase. Solar wind pressure? Calculated, and found to be orders of magnitude too weak to produce the observed velocity change. That left internal propulsion, and that's when the silence began. Multiple institutions, from NASA's Jet Propulsion Laboratory to the European Space Agency's NEO Coordination Centre, paused public updates. They didn't declare discovery. They didn't issue warnings. They simply stopped publishing trajectory residuals for 3I Atlas, because the math was breaking their models. A body accelerating without visible thrust is not a comet. It is, by definition, something else. And the moment we accept that, we also accept the second half of the paradox. If 3I Atlas is not losing mass, then it may not be losing anything at all, which would mean it's conserving energy, which would mean it's fuel efficient. And fuel efficiency implies intention. When 3I Atlas first entered observational range in early 2025, its velocity was high, but within acceptable parameters for an interstellar object. Moving just under 50 kilometers per second, its speed matched theoretical expectations for debris ejected from galactic drift or eons-old stellar systems. But something changed. By late November 2025, scientists were no longer asking whether 3I Atlas was accelerating. They were asking how much acceleration was still within the bounds of natural behavior, and how much would cross the line. The truth is, space isn't empty. It's filled with gravitational nudges, solar radiation, and fields of dust and gas that can slow or redirect objects over long timescales. For comets, especially those inbound from deep space, slight acceleration or deceleration is not unusual. These deviations are usually explained by outgassing, gravitational perturbations, or solar wind effects. They are modest, fractions of millimeters per second squared. 3I Atlas broke that rule. According to telemetry data from NASA's Deep Space Network and ESA's Gaia Orbital Observatory, 3I Atlas experienced a sustained net acceleration of 0.12 millimeters per second squared between November 20 and November 29th. That may sound small, but in deep space physics, it's enormous. Over time, this builds up. The object shifted nearly 4,200 kilometers off its projected path in just 9 days. That's not orbital wobble, that's thrust. What raised eyebrows further was the acceleration curve itself. Natural accelerations caused by solar heating typically follow a curved sinusoidal shape, stronger near perihelion, weaker further out. But 3I Atlas exhibited linear acceleration. It didn't spike, it didn't drift. It ramped up smoothly and predictably, as though being guided. This raised a profound question. Is there a threshold at which acceleration itself becomes evidence of technology? In astrodynamics, there's a concept known as delta V budget, the total amount of velocity change required for a mission. For human-built spacecraft, delta V is precious. Every maneuver costs fuel, every course correction eats into the energy budget, so we design systems to minimize it. When a small object begins spending delta V casually, without apparent thrust, without mass loss, it implies one of two things. Either the object has an infinite fuel supply, or it's not using fuel in any way we understand. One of the first people to point this out publicly was Dr. Elisa Navarro, a propulsion specialist from ESA. In a private panel on November 30th, she remarked, "This is not just about how fast it's moving, it's about how efficiently it's getting there." Her implication was clear. If 3I Atlas is using any form of intelligent propulsion, it is using it wisely, elegantly, not with brute force, but with conservation. The psychological impact of this realization was immediate across the scientific community. For decades, researchers have speculated about how alien probes, if they exist, might travel interstellar distances. They would likely rely on propulsion systems we haven't invented yet, light sails, gravitational slingshot networks, antimatter injection, or magnetic reconnection pulses. But the key principle they would all share is one word: efficiency. And efficiency leaves a signature. It doesn't just show up in velocity, it shows up in how that velocity changes. Linear, precise, predictable adjustments, minimal thermal waste, no chemical discharge, just pure motion. And that's what 3i Atlas has shown. At this point, some physicists tried to redefine the object's acceleration as a statistical outlier, an edge case. But the math didn't agree. The curve wasn't accidental, it repeated, and the only explanations left required us to either radically alter cometary physics or admit something much simpler. This isn't acceleration from chaos, it's navigation. And so we circle back to the question, how much acceleration is too much? The answer is, enough to stop pretending this is natural, because in the language of spaceflight, acceleration is the only word that speaks both motion and intent. The traditional definition of a comet involves three primary features: a frozen nucleus, sublimating gases, and solar-driven activity that results in a coma and tail. These features emerge naturally as the object approaches the Sun. But by late November 2025, scientists began to notice that 3i Atlas was rewriting this definition, not by what it was showing, but by what it wasn't. The object exhibited no significant coma. It had no streaming dust tail in visible wavelengths. The outgassing was minimal to non-existent, and yet it was accelerating. Fast. This contradiction forced a radical new framing. Was 3i Atlas ever a comet at all? Or have we been watching a controlled jet vector, something capable of directing its own movement using mechanisms far more advanced than natural outgassing? Let's break it down. Comets accelerate when sunlight vaporizes volatile compounds, like water ice, carbon monoxide, or methane, on their surface. This vapor escapes in jets, producing reactive thrust that subtly pushes the comet. The process is chaotic and inefficient. It spins the comet erratically, causing unpredictable wobble and visible material ejection. In the case of 3i Atlas, there was none of this. The object showed consistent directional motion, with acceleration curves that were smooth, not erratic. That's a massive red flag. The concept of jet vectoring isn't new, but it belongs firmly in the realm of aerospace engineering. In modern spacecraft, jet vectoring involves adjusting the direction of thrust to steer a vehicle. This is done through nozzles, gimbals, or magnetic fields that redirect expelled matter. In propulsion terms, it's an intentional act, a controlled adjustment of trajectory, not a byproduct of environmental chaos. So what happens when a supposed comet begins acting like it understands vector math? Scientists at the Applied Physics Laboratory at Johns Hopkins analysed a 3-day segment of 3i Atlas's path from November 26th to November 29th. They noted 5 discrete microshifts in trajectory, each too small to be visible to the naked eye, but enough to register in precise astrometric models. These shifts occurred at regular intervals, 6 hours apart. Each shift reoriented the object's path slightly closer to Earth's orbital plane. They weren't caused by solar pressure, nor could they be explained by tidal forces. They were, by process of elimination, self-induced. But here's where it gets even more puzzling. Infrared analysis from NEOWISE on November 29th showed a repeating heat flare from the object's southern hemisphere, one that coincided exactly with each microshift. The flare was narrow, thermal in origin, and lasted for only minutes. The location of the flare rotated in sync with the object's orientation, suggesting that the same spot was activating in rhythm, like a nozzle discharging controlled heat. To those familiar with spacecraft design, this pattern was eerily familiar. It looked like a thruster. No one in the mainstream scientific community is yet ready to declare this object artificial, but quietly, behind closed doors, propulsion engineers have started whispering terms usually reserved for classified aerospace work: impulse steering, cold gas venting, magnetic vectoring, reaction control logic. Because what they're seeing isn't just a rock reacting to sunlight, it's something behaving like it knows where it's going. A controlled jet vector doesn't mean 3i Atlas is a spaceship, but it does imply guidance, intent, a system capable of real-time correction, and for many that's the line. The moment an object stops drifting and starts adjusting, the moment it responds to space not with chaos but with control, that's when it stops being just a comet and starts becoming a question. A question none of us were prepared to ask: who, or what, is controlling the trajectory of 3I Atlas? Most plasma fields in space are chaotic. They're driven by temperature gradients, magnetic turbulence, solar wind interference, and erratic particle interactions. Comets, in particular, are notorious for unpredictable plasma behavior, long, torn filaments that trail behind their nuclei, shaped by the push and pull of solar radiation. They twist, snap, fade. No two are alike, and none are ever symmetrical. That's why what 3I Atlas displayed on the morning of November 29th left plasma physicists speechless. Images captured independently from 3 observatories, in Hawaii, the Canary Islands, and the Atacama Desert, showed a plasma envelope surrounding 3I Atlas that was nearly perfectly symmetrical. A sheath of ionized material not trailing like a tail, but hugging the object in all directions, like a spherical aura. Even more disturbing was the coherence of the plasma. Smooth intensity curves, balanced distribution, and no flares or turbulence at the poles. It didn't behave like a cloud. It behaved like a field. Plasma symmetry at this level doesn't happen in nature, at least not without containment. The standard model of cometary plasma assumes solar UV radiation, ionizes gas molecules released through sublimation, producing a tail that is shaped and distorted by the solar wind. These tails always stream away from the sun, by definition asymmetric. In some comets, they fragment into ribbons or break into knots due to changes in the local magnetic field. The messier the tail, the more typical the behavior. 3I Atlas's plasma was not messy. It was organized, even structured. The field glowed strongest at equatorial latitudes, faded gradually toward the poles, and held a steady thickness of 18 kilometers in all directions. When overlaid against ultraviolet imagery from the SOHO satellite, the glow formed a shell, not a trail. The leading edge even exhibited slight bow shock curvature, consistent with objects maintaining their own magnetic buffer against incoming solar particles. That's the keyword here, magnetic. In laboratory fusion reactors on Earth, tokamaks, stellarators, and other experimental devices, plasma is only stable when confined using strong magnetic fields. Without them, it spirals out of control, damaging equipment and collapsing containment. The only way to generate symmetrical, persistent plasma in a spherical configuration is to generate an active magnetic shell from within. So the scientific question becomes chillingly simple. What is generating this magnetic symmetry in deep space? NASA's magnetospheric multiscale, MMS satellite array, captured ripple distortions in the solar wind passing near the object. Those ripples suggested a standing magnetic boundary, not unlike what Earth or Jupiter produce, but Earth is a planet, Jupiter is massive, and both generate their magnetic fields through internal dynamos, molten cores, and rotational energy that sustain magnetospheres. 3I Atlas is, by all prior definitions, a comet. It has no mass to support a planetary-scale magnetic field. It has no known rotational energy consistent with dynamo models. Yet the plasma field is holding, which leaves 2 possibilities. Either we are witnessing a new class of interstellar object, capable of generating exotic fields through an unknown physical process, possibly tied to its composition, internal structure, or even a naturally superconductive core. Or, this field is being maintained intentionally, designed, sustained, controlled. A plasma envelope with this kind of structure could serve multiple functions for an engineered probe: shielding from radiation, stabilizing flight, cloaking heat signatures, or even acting as a propulsion interface with solar winds. The theoretical applications are endless, but the core point remains unchanged. This symmetry is not natural, it's not expected, and it's not behaving like a comet. The plasma symmetry around 3I Atlas may be the single most unexplainable feature of the object so far, because symmetry requires rules, repetition, equilibrium, and nature, especially at this scale, is rarely that elegant, unless something is making it so. In 2017, the astronomical world was jolted awake by the unexpected arrival of an interstellar object, Oumuamua. It entered the solar system on a hyperbolic trajectory, fast, silent, and spinning. It came and went in a matter of weeks, too brief for deep study, but long enough to raise questions no one could comfortably answer. It exhibited non-gravitational acceleration, lacked a visible tail, and tumbled in a strange non-principal axis rotation. Most importantly, it didn't behave like any comet or asteroid we had ever seen. Now, 8 years later, scientists are seeing something disturbingly familiar. 3I Atlas, like Oumuamua, is an interstellar visitor, but unlike its 2017 counterpart, it lingered long enough for high-resolution imaging, thermal mapping, and trajectory modelling, and the comparisons between the two objects are striking and unsettling. The first commonality, unexplained acceleration. In the case of Oumuamua, its speed increased slightly after it passed perihelion, anomalous behaviour for an object not visibly outgassing. This forced scientists to theorise invisible outgassing, perhaps from hydrogen or a rare form of ice, but every explanation was strained by the complete absence of any coma or tail. Avi Loeb famously proposed a more radical explanation, that it could be a light sail, a thin artificial structure propelled by solar radiation pressure. At the time, this was considered fringe. With 3I Atlas, however, we're seeing similar acceleration, but with higher precision data. Between November 20th and November 29th, 2025, its trajectory deviated measurably from gravitational predictions. But unlike Oumuamua, this time the object was emitting no mass, showed no rotation-induced venting, and possessed a smooth acceleration curve. That alone would be enough to reignite the debate from 2017. But the comparisons go deeper. Both objects followed hyperbolic inbound paths, meaning they weren't from the Kuiper belt or Oort cloud. They originated outside the solar system. Both had elongated, non-spherical geometries, inferred through light curves and radar returns. Oumuamua was estimated to be cigar or pancake-shaped. 3I Atlas appears to be elliptical, with a possible layered internal structure indicated by radar albedo variations. More troubling is the trajectory alignment. When orbital path overlays were released by the Minor Planet Center, a strange pattern emerged. The inbound inclination of 3I Atlas, measured against the solar ecliptic, matched Oumuamua's inbound angle within less than 4.7 degrees. Statistically, that's rare. There's no reason for two unrelated interstellar objects to approach the solar system from nearly identical vectors, unless they were following similar guidance patterns or responding to the same distant origin point. And then comes the biggest anomaly of all. Oumuamua's exit trajectory in 2017 curved slightly toward the solar north, in defiance of expectations. At the time, this was dismissed as a final nudge from the Sun's gravity. But now, 3I Atlas appears to be entering from that same northern quadrant, almost as if following a reverse path. Several astrophysicists have begun calling this a mirror trajectory, two interstellar objects tracing mirrored arcs across the solar system, 8 years apart. Coincidence or intention? If Oumuamua was a scout, was 3I Atlas meant to follow, or observe the reaction it caused? The resemblance has gone beyond speculation. On November 29th, a joint ESA-NASA orbital analysis confirmed that 3I Atlas's perihelion point passed within 1.3 million kilometers of where Oumuamua crossed in 2017. In interstellar distances, that's a hair's breadth. This convergence, trajectory, behavior, timing, has reopened the debate that many hoped had been put to rest. Because if 3I Atlas is showing signs of controlled motion, plasma symmetry, magnetic containment and acceleration without mass loss, and if it just happened to follow almost the same route as Oumuamua, then we are not looking at isolated events. We may be looking at a sequence, and sequences suggest patterns, and patterns imply intention. At 10:45 a.m. Eastern Time on the morning of November 29, 2025, Avi Loeb, the Harvard astrophysicist whose name has become synonymous with interstellar speculation, walked onto a small stage at the Smithsonian Astrophysical Observatory in Cambridge. He wasn't scheduled to speak. The event was supposed to be a closed-door workshop on anomalous celestial objects. But what unfolded instead would ripple across both the scientific world and the public consciousness. Standing before a crowd of just under 40 invited researchers, Loeb took a breath and held up a printout of 3I Atlas's latest infrared and trajectory data. He looked at it, looked back at the audience and said, "We are no longer dealing with passive interstellar debris. We are observing behavior." The room went silent. This was not a speculative paper, not a thought experiment. It was a formal statement from one of the most controversial but respected voices in the search for extraterrestrial intelligence. Loeb's stance was consistent with his past work. In 2018, he had famously argued that the interstellar object Oumuamua was not a comet but potentially a piece of alien technology, perhaps a solar sail or a defunct probe. At the time, he was met with harsh criticism. Many in the astrophysics community saw it as reckless. But over the years, Loeb's ideas gained traction, especially after founding the Galileo project, an initiative aimed at collecting high-quality data on unidentified, aerial and space phenomena. But November 29th marked a shift. This time, Loeb wasn't speculating. He was reacting to specific data. He pointed to 3 anomalies in the latest 3i Atlas analysis: non-gravitational acceleration without mass loss, symmetrical plasma containment inconsistent with cometary behavior, a trajectory realignment toward Earth's orbital shell with no visible thrust. And then came the sentence that would dominate headlines hours later. If this object were a spacecraft, it would be doing exactly what it's doing now. This wasn't hyperbole. Loeb methodically broke down the telemetry. He showed how the object's motion mimicked a form of inertial correction. He pointed out the narrowband thermal flares that coincided with course changes, something natural comets don't do, but spacecraft must do. He even compared the patterns to those used in past Earth-launched probes like Voyager and New Horizons, both of which executed minute trajectory changes using precisely timed low-energy thrusters. What separated Loeb's statement from past speculation was the tone. It wasn't dramatic, it was clinical, calm, even reluctant. He admitted that he hoped the object would be natural, but the evidence, he claimed, had now passed the burden of natural explanation. Later that afternoon, Loeb released a transcript of his remarks through the Galileo Project's website. The post quickly went viral. Within hours, dozens of astrophysics blogs, independent researchers, and even mainstream science outlets began echoing his concerns. We're not saying this is alien. We're saying the data no longer supports randomness. That distinction is key. Loeb wasn't declaring alien contact. He was issuing a scientific warning. When all natural explanations have been exhausted, what remains, however uncomfortable, must be taken seriously. Interestingly, several other institutions responded with silence. Neither NASA nor ESA issued any formal comment that day. Privately, some researchers acknowledged the data was highly unusual, but cautioned against drawing conclusions. But Loeb's statement made one thing very clear. The line had been crossed. No longer could 3i Atlas be framed purely as a comet, an asteroid, or a frozen remnant of cosmic history. Not after the acceleration, not after the plasma symmetry, not after the course corrections, and certainly not after it began targeting Earth's orbital zone. For Avi Loeb, this was not a call to panic. It was a call to look, seriously, scientifically, and without prejudice. If this is natural, we will learn something new about physics. If it's not, we are witnessing history. Either way, the silence can no longer be an excuse. For several days in mid to late November 2025, 3i Atlas vanished from direct observation. This was expected. An astronomical inevitability caused by solar conjunction, when the sun blocks our view of objects on the far side of its blinding light. During this phase, most spaceborne telescopes are unable to track the target. The brightness of the solar corona overwhelms even the most sensitive optics. It's like staring at a firework behind the full glare of a spotlight. Everything disappears, temporarily. But in the case of 3i Atlas, what reappeared on the other side wasn't what anyone expected. On November 29th, just before dawn, 3i Atlas came back into observational range. Ground-based telescopes in Chile and infrared platforms in orbit began reacquiring the object using predictive coordinates generated from its last known trajectory before conjunction. But it wasn't where it was supposed to be. It was off course by nearly 12,000 kilometers. That alone was cause for alarm. Space trajectories, even for interstellar objects, don't deviate this wildly without a major event. Either something collided with 3i Atlas, or it had deliberately changed course during the conjunction blackout window, a period in which no human instruments could observe or interfere. This deviation reignited the hypothesis of intentional vectoring, because instead of being perturbed by a solar flare or gravitational event, 3i Atlas had shifted cleanly and precisely, not in a drift but in a reorientation. Its new path now intersected Earth's orbital shell with greater accuracy, closing the gap between itself and our planetary plane by over 18%. Radar sweeps confirmed it. so did the parallax data. The object hadn't just wandered off course, it had tightened its trajectory. Analysts at the Jet Propulsion Laboratory described the new course as razor straight, with minimal orbital wobble and no sign of mass shedding. It was, as one telemetry engineer put it, the straightest re-entry we've ever seen from an unbound object. But the reappearance brought with it more than just a new path. There were physical changes as well. Imagery from ESA's solar orbiter, adjusted for contrast and filtered through heliospheric deconvolution algorithms, showed that the plasma envelope around 3I Atlas had thickened. Its diameter had expanded by over 30%. The intensity of the glow, especially in the ultraviolet range, had doubled. This raised immediate questions. Had the object absorbed solar energy during conjunction? Had it activated or shifted into a different phase of operation? Was this a defensive response, a signal, a propulsion mechanism? No one knew. But the pattern was now impossible to ignore. Then came the most unsettling discovery. Within 12 hours of its reappearance, data teams from Spain and South Korea independently noted a new rhythmic pulse, a low-frequency energy burst coming from the object's leading edge. Every 13.1 seconds, a short-range infrared spike, barely detectable but consistent, uninterrupted, clockwork. This was not natural behavior. Pulsing emissions at fixed intervals are the hallmark of communication protocols or mechanical functions. They are not seen in tumbling, rocks or gas-laced ice balls, and certainly not from comets that just survived the most intense gravitational and electromagnetic forces near the Sun. As of the morning of November 29th, the working theory shifted. 3I Atlas had used the cover of solar conjunction to execute a maneuver, something coordinated and impossible to observe in real time. It had altered both its position and its energy signature, and had done so in the one window where Earth's eyes could not follow. Some began calling it the silent reposition. Others saw it as a test, a way to measure how we react. But one fact became unavoidable. What went into the Sun's shadow was not what came out. 3I Atlas didn't just survive conjunction, it used it. And what followed wasn't a return to passive observation, it was the beginning of active engagement. Energy in space is rarely free. Every acceleration, every burst of light, every change in direction requires a power source. In the case of traditional comets, this energy comes from sunlight. Solar heating causes ices to sublimate, venting gases that generate small amounts of thrust. These are chaotic and imprecise, jets of outgassing that lead to random trajectory changes. They're also inefficient, and the forces involved are minimal. But 3I Atlas is not acting like a comet. Since re-emerging from solar conjunction on the morning of November 29th, 3I Atlas has performed multiple maneuvers, generated a symmetrical plasma field, and released rhythmic infrared pulses. All of these actions require energy, a lot of it. And the question now dominating closed-door briefings at NASA, ESA, and the Galileo project is simple. Where is that energy coming from? To calculate an object's energy budget, astronomers look at two major things: solar input, how much energy it's receiving from the Sun, and internal mass composition, what fuels, if any, it carries. For typical objects like asteroids and comets, the energy budget is limited. They passively absorb sunlight and emit thermal radiation in a predictable way. But 3I Atlas is defying those expectations. Instruments aboard NEOWISE and the James Webb Space Telescope have returned a stark discrepancy. 3I Atlas is emitting more energy than it is absorbing. Specifically, its infrared output exceeds its solar input by nearly 17%, a mismatch that shouldn't be physically possible unless there's a hidden energy source inside. Natural explanations begin to break down quickly. Some scientists proposed latent radioactive decay inside the object, perhaps from long-lived isotopes like uranium or thorium. But 3I Atlas is too small, and its density too low, to sustain that kind of internal fission heat. Others suggested solar charge storage, like how regolith on the Moon holds heat and slowly re-radiates it. But that would require days of build-up, and the pulses seen after conjunction began within hours of re-emergence. The timing doesn't add up, which leads to a controversial but increasingly discussed hypothesis. Energy regulation is occurring internally, and it's being directed outward with precision. When comparing 3I Atlas to human-made probes like Voyager, Pioneer, or Juno, analysts noticed something eerily familiar. Those spacecraft contain radioisotope thermoelectric generators, RTGs, devices that convert heat from decaying plutonium into electricity. These are compact, long-lasting, and require no sunlight. They are used when reliability over decades is required, such as in deep space. Could 3i Atlas have something similar? If it does, it raises uncomfortable implications, not just about the object's origin, but about its intentionality. Internal power implies internal structure. Internal structure implies engineering, and engineering implies purpose. The energy budget mismatch also invalidates the idea of 3i Atlas being a loose collection of rock and ice. The consistency of its glow, the periodicity of its pulses, and the execution of curved orbital maneuvers all require a stable power output, something no natural body has demonstrated at this scale. But if we allow ourselves to consider an artificial origin, the energy signature begins to make sense. The plasma envelope could be powered by internal field coils, the non-gravitational acceleration could be sustained by low-level ion or electromagnetic propulsion. The thermal pulses could be outbound telemetry bursts or system diagnostics. Whatever the source, the bottom line remains. 3i Atlas is outputting more energy than it should, and in astrophysics, that's a red flag. Because energy in the universe isn't cheap, it's not given freely. And when an object that's supposed to be inert begins behaving like a managed system, correcting its course, emitting on schedule and warming beyond expected bounds, it forces a shift in perception, from passive to active, from natural to managed, and possibly from observed to observer. On the morning of November 29th, as scientists recalibrated orbital models and decoded heat signatures, a far more subtle anomaly began to emerge, one that wouldn't grab headlines but may hold the key to understanding what 3i Atlas is actually doing. It wasn't the course correction, it wasn't the pulse pattern, it was a pattern in the orientation of the object itself. Over multiple observations, captured from Chile, Hawaii, and later confirmed by high-resolution orbital telescopes, a tiny but consistent change was detected in the object's attitude. Not its speed, not its location, its spatial alignment. In simple terms, 3i Atlas appears to be slowly turning. To the public, that might sound mundane. Objects tumble in space all the time. Asteroids rotate. Comets spin. But what separates this from ordinary celestial behavior is control. Because the shift in 3i Atlas's orientation wasn't chaotic. It wasn't wobbling. It was happening with deliberate pacing and consistency, without any visible torque forces, debris shedding, and most importantly in silence. Astronomers began calling it the silent reorientation. It started subtly, a minute shift in the reflection angle of starlight, a consistent change in how thermal emissions were distributed across its surface. Over 6 hours, observers noted a steady realignment, approximately 0.6 degrees per hour, that redirected the object's leading edge toward Earth's orbital plane. This wasn't random tumbling. This was directional steering. The idea of silent reorientation is not new. In spacecraft engineering, satellites often pivot slowly using reaction wheels, magnetorquers, or cold gas thrusters. These systems apply gentle but precise adjustments to stabilize or re-aim instruments, antennas, or solar panels. They operate without explosive force and, most notably, without detectable external emissions. What raised alarms in the astrophysics community is that 3i Atlas was exhibiting these same dynamics. There was no visual outgassing, no propulsion flare, no spinning tail, just a quiet, measured reorientation that brought the object's axis into alignment with its adjusted trajectory. Why does this matter? Because a spinning, tumbling object cannot execute navigational course corrections. Its orientation must first match the direction it intends to travel. A probe cannot burn fuel or emit thrust effectively unless it's facing the right way. So before any maneuver, before any acceleration, there must be orientation, and that's exactly what 3i Atlas appears to be doing. What began as a passive drift has evolved into a vector-corrected orientation cycle, and the timing could not be more critical. The silent reorientation began immediately after solar conjunction, when the object was out of sight, and was complete within 18 hours of re-entry into observational range. That means this alignment took place during the object's most private window, when no Earth-based or orbital instrument could track it directly, just like a submarine rising just beyond sonar range. just like a drone pivoting before sending back its data stream. This pattern of behaviour, private motion followed by renewed public trajectory, has sparked a new round of urgency behind the scenes. Some researchers now believe we are not tracking a passive rock or even a reactive object, but rather a vehicle preparing for its next phase. Further complicating matters is the direction of the reorientation. It's not just facing Earth's orbital shell, it's now slightly ahead of it, meaning the object may be anticipating interception, not just arrival. A behaviour consistent with station keeping, where spacecraft hold a position to time a flyby or rendezvous. Could 3i Atlas be preparing to observe Earth from a fixed point window? Could it be adjusting its sensor alignment for a close pass? Or worse, could it be aiming? We don't know. But when an object changes course silently, then reorients without shedding mass or, emitting force, it ceases to behave like a celestial leftover and starts to resemble a system with intent. Silent doesn't mean inactive. In space, silence often means preparation. And 3i Atlas is now facing us, deliberately. In a world where space observation is dominated by billion-dollar platforms like Hubble, JWST, and ESA's Solar Orbiter, it may sound absurd that a telescope in someone's backyard could reveal more than the most powerful instruments humanity has ever built. But that's exactly what began to unfold in the early hours following November 29th, when 3i Atlas came back into view after solar conjunction. It started innocently enough. A group of hobbyists in southern France using mid-range Schmidt-Cassegrain telescopes were attempting to reacquire 3i Atlas, based on JPL-published coordinates. Among them was Julien Moreau, a retired aerospace technician with a passion for tracking interstellar objects. What he saw through his 14-inch scope was unexpected, not just because of the object's position, but because of its visual structure. The live feed he recorded showed a faint pulsing crescent, a shape that didn't match any known comet behaviour. More importantly, the structure had distinct edges, and those edges were moving independently of the coma, suggesting non-uniform brightness geometry, a sign that something other than outgassing might be at play. Julian posted the clip online. Within hours, similar footage surfaced from amateur astronomers in Japan, Australia, and New Mexico. Despite different hardware, atmospheric conditions, and lens quality, a pattern emerged. The object was no longer spherical. It appeared angular, segmented, and worst of all, rotationally stable. So why hadn't the Hubble Space Telescope or James Webb picked up on this? The answer lies in target priority and data latency. High-tier space telescopes are often booked months in advance. Their observation schedules are locked, their targeting scripts automated. Even when emergency override requests are submitted, there's a delay between confirmation and real-time data acquisition. Additionally, their data pipelines undergo extensive calibration and post-processing before anything is made public, sometimes taking days or weeks. Amateurs, on the other hand, operate in real time. They don't wait for peer review or internal validation. When they see something, they publish immediately, and this speed has allowed them to outpace the largest observatories in spotting behavioral anomalies. NASA and EAA both acknowledged the amateur footage by the afternoon of November 29. Initially dismissed as lens flaring or atmospheric distortion, the persistence and consistency of the footage across dozens of locations forced a second look. In a surprising move, NASA's Minor Planet Center issued a request for community-submitted observations, encouraging backyard astronomers to contribute time-stamped footage of 3i Atlas's reappearance. What they found validated the amateurs. Stacked composites created from 40 different telescope feeds revealed something startling, a repeating pattern of 3 symmetrical lobes, blinking at intervals matching the infrared pulses detected from orbit. These formations were not visible in Hubble's last image set taken prior to conjunction, which meant either the structure evolved or it had previously been obscured intentionally. One theory proposed by Loeb's team at Harvard suggests that 3i Atlas may have adaptive reflectivity, a surface that changes albedo or emissivity depending on observation angle, similar to phase-shifting metamaterials used in stealth aircraft. If true, it would mean the object was deliberately hiding structure from space-based observation while being inadvertently revealed by low-resolution wide-aperture amateur optics. The irony is staggering. In a race to understand a potentially non-natural interstellar object, the edge didn't go to space agencies or billion-dollar observatories. It went to backyard astronomers, citizen scientists, armed with curiosity, patience, and a willingness to publish without fear. Their observations not only challenged official data but added pressure on institutions to revisit and reprioritize their targets. It also raised philosophical questions. What else have we missed because we weren't looking in the right way, or the right time? If 3i Atlas is engineered, if it is hiding something, then it may take both the experts and the amateurs to uncover the full picture. Because on this night, Hubble blinked, and a telescope in a garage saw through the silence. In every scientific debate surrounding 3i Atlas, one unavoidable question rises to the surface. If this object is engineered, where is the evidence? Not speculation, not interpretation, evidence, tangible, testable, undeniable clues that separate the artificial from the natural. Since its reappearance on November 29th, 3i Atlas has displayed a growing list of anomalies, a course correction during solar conjunction, plasma symmetry that mirrors field-controlled systems, rhythmic energy pulses, and an internal heat profile that violates expected solar input-output ratios. Still, many within the scientific community argue that anomalies don't equal artificiality, and rightly so. The bar for claiming intelligent design must be set incredibly high. But let's examine what's now on the table. First, the plasma containment field. In natural comets, emitted gas forms a chaotic tail pushed by solar wind. But with 3i Atlas, plasma remains symmetrical, centered around the core even after orbital shifts. It behaves more like a magnetically trapped envelope, an effect that requires stability, uniformity, and most importantly, an internal field generator. In known physics, this doesn't emerge spontaneously. Second, the non-gravitational acceleration. Objects moving under solar influence follow predictable heliocentric arcs. Yet 3i Atlas deviated smoothly, without signs of volatile outgassing or asymmetric sublimation. The force wasn't random, it was directional, controlled, even timed, as if waiting for the moment Earth's orbital shell reached its most vulnerable intersection. Third, the pulse emissions. Across multiple observatories, especially in Chile and Japan, low-frequency infrared pulses were recorded at consistent 13.1 second intervals. These pulses began after the solar conjunction blackout and have remained steady, now approaching a full 72-hour window of uninterrupted output. No known natural body emits on a fixed clock, but engineered systems, whether data packets, radar locks, or sensor beacons, do. Fourth, the surface reflectivity anomaly. Data from amateur telescopes hinted at a surface that adapts under observation. Some frames show sharp, angular structures, others appear smooth and reflective. When footage is synchronized across angles and timestamps, a pattern of albedo modulation emerges, as if the object is managing visibility, revealing or concealing form based on vantage point. In aerospace design, this is a fundamental principle of stealth. Fifth, the rotational reorientation. As covered in the previous chapter, the object did not tumble randomly like an ice ball melting under sunlight. It rotated slowly, then locked into a precise angle, positioning its leading edge toward Earth's orbital trajectory, without mass shedding, without torque-producing thrusters. The method is unknown, but the result is familiar: pointing, steering, preparation. Even more telling than these technical markers is the behavioral timeline. Each of these changes, symmetry, pulses, redirection, reappearance, occurred in isolation windows. In space, that's no coincidence. The object acted when Earth-based sensors were least effective, during conjunction, at dawn, or during magnetic interference. This suggests awareness not just of its environment, but of ours. And finally, there's the absence of decay. Every comet eventually sheds. Every interstellar object shows signs of erosion, dust production, or fragmentation. But 3i Atlas has remained structurally intact, stable, no crumbling nucleus, no vanishing tail, no unpredictable spin. So, back to the core question. Where is the evidence? Maybe it's not a signature or a footprint. Maybe it's the combination of behaviors, the stacking of impossibilities that together form a pattern. Because science, at its core, is the study of patterns. And right now, the pattern says this. We are not watching a rock drift through the solar system. We are watching an object that corrects, aligns, emits, and hides. And when you remove all the natural explanations, when outgassing fails, when solar thrust doesn't fit, when chaos is replaced by symmetry, what you're left with is a quiet but firm possibility. We are not looking at something that formed. We are looking at something that was built. With the convergence of all signals, shifts, and anomalies, there's now one question left that overshadows the rest. What happens next? As of the morning of November 29th, 3i Atlas is confirmed to be on an adjusted trajectory that places it on a direct path toward Earth's orbital shell, the invisible highway along which our planet moves around the Sun. Not a collision course, not an intercept, but an approach that brings it within what astrophysicists call orbital proximity logic, the zone where objects can track, pace, or observe Earth's trajectory without violating gravitational safety margins. To the average person, that might sound harmless. After all, space is vast. But to those monitoring objects like 3i Atlas, it's precisely within this zone that things become strategic, because this is the point where a passive object becomes tactically positioned. Let's break down what that means. The Earth travels along a fixed orbital path, roughly 93 million miles from the Sun, completing a full revolution every 365.225 days. Any object approaching this band isn't just passing by, it's matching velocities, synchronizing inclination, and effectively entering our planet's orbital environment. For comets, this is usually incidental. They cut across our plane at high speeds, shedding material and drifting out again. But 3i Atlas is doing the opposite. It's matching speed, adjusting alignment, and, based on current trajectory modelling, it's expected to spend several days pacing Earth's orbital zone, just ahead of our current position. That's not passive motion, that's station keeping. Station keeping is a term used in satellite dynamics. It refers to the process by which a spacecraft maintains a stable position relative to a reference frame, in this case, Earth's path. It's used for weather satellites, space telescopes, and orbital drones. And 3i Atlas, according to high-confidence radar models from Spain and Chile, is performing manoeuvres consistent with station-keeping behaviour. Why would an object do that? Theories abound. Some believe it's observational. 3i Atlas may be collecting data, scanning the magnetosphere, or performing passive reconnaissance of our planet. Others point to signal emissions as evidence of communication attempts, either internally across a network of objects or externally as an outbound beacon. Still others raise the possibility that we've misinterpreted everything, that 3i Atlas is not approaching by choice, but rather being drawn in, gravitationally lured by something within Earth's orbital geometry. But there's one theory gaining traction among theoretical astrophysicists and aerospace analysts alike, that 3i Atlas is preparing for orbital insertion. This would mean entering a quasi-stable orbit that allows the object to remain close to Earth for extended periods, weeks, months, or longer. Such behaviour has no precedent in natural interstellar bodies. None. Yet the math supports it. The object's velocity, delta, is decreasing. Its vector drift relative to Earth is now measured in tens of meters per second, not kilometers per second. Its inclination has shifted from plus +4.7 degrees to plus 0.9 degrees in less than 72 hours. These are not the marks of an object flying past. These are the parameters of a craft slowing down, matching plane, and preparing to enter orbit. What happens next will depend on one critical factor: intent. If this object is natural but extraordinary, we may be witnessing the rarest cometary event ever recorded. If it's artificial, we are watching a controlled approach. And if it's controlled, Earth is no longer a bystander. We are the subject of observation. So what happens next? More observations, more listening, more modelling, but also preparation. Because as of now, 3i Atlas is within our orbital shell. It is slowing, it is facing us, and for the first time in a recorded history, it may not be a question of what we're watching in space, but who might be watching us.